So I hope all of us are doing fine. My name is Ernest, and this is Ernest Sciences and Mathematics TV channel. Before you proceed, I'd like to request our members to kindly subscribe to our channel and also open the links that I normally put in the description boxes of various videos. And of course, they are going to contain various topics which are related to the topic under discussion. Now, in this case, I'm going to look at the concept of entropy and pressure. And this basically is a representation of these two states in terms of partition function. Now, in our previous videos, we had done the concept of internal energy and Helmholtz energy. And of course, from the previous relationship that we had basically mentioned that we can represent the Helmholtz free energy using this function, which is A. And this basically is Helmholtz free energy function. Sorry for that. This holds free energy function that's given in terms of A, and this in terms of an algebraic representation or an equation, this was given in terms of internal energy minus the product of absolute temperature and entropy given as such. And of course, we can be able to describe the concept of entropy from this specific relationship by making S the subject of our formula in this specific equation. So therefore, we're going to have internal energy minus Helmholtz energy, and of course, we're going to have this one given in terms of T, and this is going to give us the relationship between Helmholtz energy and entropy. Now, later on, we're going also to see the aspect that is describing pressure. But of course, from this particular case, I'm going to use the previous equation we have had on internal energy. And in that case, of course, on the Helmholtz energy that we had done in terms of partition function for these two specific equations. And in this case, I mentioned that basically our partition function is going to constitute all the summation of energies which are thermally accessible at a particular temperature. And at the given giving it in terms of negative UI. And of course, this formed a basis for us in representing various other modern. Therefore, in this case, I'm going to use the change in internal energy, which are given in terms of U minus U not given as such. And I'd said that this basically is going to be considered from the absolute zero value, and therefore at a higher temperature that is going to dictate the number of energy levels which are going to be occupied. So this was given in terms of kd, the square of T, and of course the partial derivative of the natural log of Q with respect to T, and we said this is under the aspect of a constant volume given as such. And the Helmholtz free energy from representation of Helmholtz free energy in terms of a partition function. We are given this one in terms of negative kBT, and then the natural log of Q given as such. So these two basic changes are going to give us the value for U and T, U and A. And of course, we're going to do a substitution in order for us to find our final representation for the representation of entropy in terms of the partition function. So therefore, perhaps I can do away with this. So we're going to have entropy represented in terms of this specific representation for the Gibbs Helmholtz free energy, which is going to be given in terms of the natural log of K, the natural log of Q, and then negative K. So if we look at this specific operation, we're going to have the numerator subtracted of this is internal energy minus Helmholtz free energy, but Helmholtz free energy is a negative kBT natural log of Q. Therefore, we are going to have this one given in terms of can it be given either ways in terms of the first one or the second one, and therefore I'm going to have it given as kBT, and that is going to represent our internal energy, and this is going to be the square into the partial derivative of the natural log of Q over T, and this under constant volume, and then plus. So I'm going to have this one given as this, and then I'm going to have this one plus this specific second one. So there's a simplification that I'm trying to avoid so that we cannot get caught up or mixed up in this case. So I'm going to have the KB. So this is going to be KB, the natural log of Q, given as such. So if we try to look at this, this basically is going to be under a constant temperature, which is going to be given as all over T. So therefore, this is going to simplify and remain with this specific aspect of a temperature being given in terms of a T. So therefore, I'm going to have my denominator given as that. So that's how it simplifies out, and this is specific sign that is given in terms of course, a positive value given as such. So this is how we can come up with a representation of entropy in terms of a partition function. And of course, we're going to see that for the two values of U naught and A naught, they're going to be considered, of course, from the absolute value, which is the absolute zero, which we had said, for the values of entropy, and of course, for the values of internal energy given in that specific, or the moles free energy and the internal energy given in that specific order. Now, I mentioned basically combined this one with the concept of, so I hope that we have understood this specific derivation from the basic one of representation of a moles free energy, and how we can arrive at the aspect of entropy, which is represented in terms of a partition function. Now, if you look at the aspect of pressure, I've intentionally combined this one with pressure because we have already done some aspect of pressure, and therefore it's going to be a short description of a representation of this pressure in terms of a partition function. Now, for pressure, we're going to have the relationship, of course, from the concept of pressure, and this is the relationship that that connects the equation of pressure to the moles free energy. And of course, I've given this particular representation. So for pressure, we're going to have it given in terms of the partial derivative of moles free energy and volume. And this is going to be under constant temperature in that specific case. So we're going to, I'm also going to put a link of this specific video in the description box. So kindly check so that we are able to be at par with this specific derivation. So we're going to have this one as Kp, and this is going to be as the natural log of Q all over derivative with respect to volume, and that's going to be under constant temperature. So this is going to be the partition function of the fashion of pressure, considering the equation that connects moles free energy to pressure using this specific relationship. So basically that is it for entropy and pressure, and these are the two thermodynamic variables which we had mentioned, which of course can be expressed in terms of a partition function. So catch us in our next videos. We're going to look at that aspect of thermochemistry, and that's going to play a vital role in us understanding various applications that we come across, especially in the problem set. So that is it for now, guys. Kindly subscribe to our channel and engage us in the comment section for more. So that is it. Bye. God bless you. Catch us in our next video.